Good morning to everybody, and good afternoon and good evening to the rest of the people around the world. So first, I would like to thank Thaisa and the organizers for this very nice conference and for the opportunity to come to Australia, which is my first time here. So I was asked to talk to you about astrochemistry. So I will switch a little bit from more the physical aspects to the chemical ones. So I will speak a little bit about molecules mostly. So let's start. So the first point I would like to do, well, here you have the cycle of matter. The first point I would like to do is that just as all of us are made of atoms that have been cooked some time ago inside a star, there is also some chemical complexity that is taking place around evolved stars that may survive the whole life cycle of matter and will incorporate at some point in planetary systems. We know that at least for the dust. So the first point I would like to make is that, as I was telling you before, that that dust grains that are formed in around the evolved stars, we know that they survive the whole life cycle of matter because we have found here in our solar system dust grains that have been synthesized around AGB stars in a long time ago. And also, we know that some large molecules of the family of benzene, PAHs, and fullerenes that have been synthesized also around AGB and post-AGB stars. We don't know exactly how, but we know that they survive also the whole lifetime of matter. So at some point, the point here is that the chemical complexity, not only the nuclei that we are made of, but also the chemical bonds between these atoms, may that is cooked here around AGB stars may survive and may play a role in when forming a planetary system. So let's focus a little bit. You know more or less the scheme of what is a circumstellar envelope around AGB star. We have the inner regions where we have high density, high temperature. We expect chemical equilibrium to happen. We also have the dust formation at some point, a few stellar radii, and then in the outer regions we have a different type of thing going on, mainly photochemistry. So on the physics, you have already heard a lot that basically the scenario that moves the envelope has to do with the radiation pressure on dust grains and the pulsations. You already heard, so I will not focus on that. I will focus more on the chemistry. And on the chemical side, there are a couple of important dichotomies. One is related to whether you have an oxygen-rich or carbon-rich AGB star. That will make the chemistry completely different. And the other dichotomy I would like to stress is the inner regions compared to the outer regions, because the type of chemistry that is going on in these two types of regions is completely different. Here is more related to chemical equilibrium, and here is more related to photochemistry. So I will basically speak about what happens very close to the stellar surface, and I speak a lot about chemical equilibrium. Also about how dust is formed at some point, and also about what happens in the outer layers of photochemistry in the outer parts. So that will be more or less the outline of the talk. So about just to show you a little bit about what is the typical molecules we find in these circumstellar envelopes. Here you have the inventory of molecules, nearly 100 molecules found in one famous evolved stars, the IRC plus 10^16. So you have here the abundance relative to molecular hydrogen, and then you have in different columns the different families. Here you have oxygen-rich species, carbon-rich species, a lot of ones containing nitrogen, also a lot of, a few containing sulfur, silicon, phosphorus, and here you have in this column all molecules containing metals. That this has increased a lot in the recent years, and it's curious because this is the only type of environment in a space where we can find molecules containing metals. Normally in the interstellar medium, temperatures are so cold that you don't find molecules containing metals because most metals are supposed to be locked on dust grains. A few years ago, there has been a few discoveries of molecules containing metal, mostly sodium chloride, around star-forming regions also, but they resemble a lot the physical conditions that we can find here, but basically they are high temperature and high density, okay? So this is concerning carbon-rich stars. Sorry. Concerning oxygen-rich stars, the inventory is much lower, and this has to do with the fact that the chemical properties of the carbon atom that has the ability to form bonds with other carbon atoms and has the ability to form very complex molecules. In the case of oxygen-rich stars, you still can find some peculiar and exotic molecules, but the richness, let's say, normally it's poorer. So these are the molecules detected around 8 tau plus some other containing metals. Also, you have here a different type of metal containing molecules, mostly oxides. So I will start with what happens in the inner regions. So I will speak about what's going on very close to or even at the stellar surface, where typically the conditions, temperature and pressures we can find there are of the order of 2000 or even higher temperatures, and the pressures are the order of 0.1 millibar or 1 millibar. So normally at these conditions, we expect that chemical equilibrium would be a good approximation of the chemical composition that will be happening here. But let's take a look to what happened with this the predictions of chemical equilibrium. Okay, so let's start with what is the reservoir of oxygen. Here, what you can find is basically the abundance relative to molecular hydrogen, or the mole fraction, as a function of the carbon to oxygen ratio. So here you have ratios higher than 1. So this is carbon rich in this region. And here you have oxygen rich case. Okay. So about the oxygen, where is oxygen located? Is basically located in basically here the important point are these lines. That the colors are just to make the figure a bit more fancy. But basically, the abundance of carbon monoxide is very high. It basically takes all the carbon or oxygen, and it does not depend much on whether you are carbon or oxygen rich. So what do the observations tell you? So basically, the abundance derived for CO agree very well with the predictions from chemical equilibrium. So on this side, chemical equilibrium is a very good approximation for what's going on, and in fact, it describes very well many of the properties, and not others, as we will see. So in this case, we have a good agreement, so a success of chemical equilibrium. Okay. So in fact, I have to say that for carbon monoxide, in fact, we don't determine the abundance, because we in fact use carbon monoxide to estimate the mass loss rate, but just because we cannot observe molecular hydrogen. So normally this is not really an observed parameter, but a few years ago, I mean a couple of years ago, these guys, a collaborator of mine, could observe molecular hydrogen using SOFIA in this famous carbon-rich star. So with this rotational line of molecular hydrogen, they were able to estimate the mass loss rate using molecular hydrogen and not carbon monoxide, and they were able to estimate the abundance of carbon monoxide, which in fact was around 6 times 10 to the minus 4, which is in the order of what is predicted. Okay, so let's move on. The other important molecule containing oxygen is water. And you can see here that in the case of you have oxygen-rich star, the abundance of water is very high, of the order similar to the one of carbon monoxide. But when you go to the carbon-rich case, the abundance of water drops by many orders of magnitude. So what do the observations tell? For the oxygen-rich case, the abundance derived for water agree very well, again, with the predictions from chemical equilibrium. So we have a success here. But in the case of carbon-rich stars, the abundance derived for water is of the order of 10 to the minus 6, which is many orders of magnitude above the predictions from chemical equilibrium. So in this case, we have a failure of chemical equilibrium to describe what's going on. This was mainly driven by observations with Herschel, in which Lin was also involved. And water was observed in not just one, but many carbon-rich objects, and always with this range of observed abundance. So here, clearly, chemical equilibrium does not fit. What about of carbon? So carbon, again, will be locked mostly on carbon monoxide. And also in the carbon-rich objects, acetylene will take up a lot of carbon. While in oxygen-rich stars, you expect that the abundance drops dramatically. So in fact, if someone comes with an observation of acetylene in an oxygen-rich star, that will be a great surprise, something to look at. About the abundance derived in carbon-rich objects, again, they agree very well with what chemical equilibrium predicts. So here we have a good match. So in this case, chemical equilibrium works very well. Sorry. And this observed abundance of acetylene came mainly from infrared observations, because it has no dipole moment, cannot be observed at radio wavelengths. So moving on for nitrogen, here most of the nitrogen is predicted to be locked in molecular nitrogen. In this case, we cannot observe it because it's non-polar and has neither infrared spectrum. So here we expect that chemical equilibrium is predicting things properly, but we cannot contrast with observations. In the carbon-rich case, also a molecule that takes a lot of nitrogen is HCN. And you see here that the predictions for ammonia are very low, no matter whether you are carbon-rich or oxygen-rich. Okay, so let's see what observations tell us about HCN. The range of abundance observed agree very well, again, with the predictions from chemical equilibrium. So in this case, we have a good match. For the oxygen-rich case, the abundance observed for HCN, again, do not match at all. We have here a discrepancy of many orders of magnitude. So in this case, chemical equilibrium is failing. And also in the case of ammonia, as Katan has worked on this subject, we know that no matter also whether you have some differences in the abundance, whether you are carbon or oxygen rich, but again, we have a discrepancy of many orders of magnitude. Moving a little bit on sulfur, a molecule that takes a lot of sulfur in carbon-rich objects is CS, carbon monosulfide, but not in oxygen-rich stars. So the predictions for carbon-rich stars agree very well with the observations, but in the case of oxygen-rich stars, again, we have some discrepancy with what chemical equilibrium predicts. Okay. Yeah, the last one. For silicon, silicon monoxide is predicted to lock a lot of the silicon in oxygen-rich stars, somewhat less in carbon-rich stars. Again, the observations agree well with the values predicted, with the abundance predicted by chemical equilibrium, and also for the carbon-rich case. And about the silicon dicarbide, the abundance also agree relatively well with the abundance predicted by chemical equilibrium. Okay. So you have seen that depending on the molecule, we have that chemical equilibrium works pretty well. So it reproduces pretty well what then we observe. But for some other molecules, the discrepancy is very, very, very large. So many orders of magnitude. So here, to give you a taste of what are from where this range of observed abundance come from, they come from mainly from single-disk observations of many, many different objects. Here we have some, first we'll focus on ACN, this is work by Frederick Sawyer, who unfortunately passed away some years ago, but his work inspired me a lot on the area of evolved stars. He made great jobs. So here you have the abundance of HCN relative to molecular hydrogen as a function of the density measure, which is basically the mass loss rate divided by the expansion velocity. So basically you see that for carbon-rich stars, the abundance are, let's say, around 2 orders of magnitude higher than for oxygen-rich stars. Here, the color code has changed. So here in red, we have carbon rich, and in blue, you have oxygen rich. Here, you have the same, but that CS is more abundant in carbon rich than in oxygen rich. Same for here, silicon dicarbide, only in carbon rich, because we have, for the moment, no detection of this molecule in oxygen rich stars. And for SIO. So this is to give you a little bit an idea of what are the typical abundance observed. You see here a dispersion in the abundance depending on the object. It may be up to 1 or 2 orders of magnitude, the difference, but still it's much lower than the big discrepancy we have with chemical equilibrium. So this dispersion of abundances cannot explain the discrepancy, okay? So what's going on here? So the conclusion is that at some point there must be some deviation from chemical equilibrium happening in the very inner regions close to the atmosphere of AGB stars. But as I told you, the temperatures there and the pressures are relatively high. So at these conditions, we should expect that chemical reactions should be relatively fast. And that means that when chemical reactions are fast, they should reach the thermodynamic equilibrium relatively fast. So just to give you an idea, for this range of pressure and temperature, the density is around 10 to the 14 particles per cubic centimeter. So adopting a rate coefficient of the order of 10 to the minus 10, which is in the upper side of the typical rate coefficients for chemical reactions, we arrived to the conclusion that the reaction time for example, for a reaction, for a species reacting with molecular hydrogen is of the order of 0.1 millisecond. So this gives you an idea. Of course, this is a kind of upper limit. I mean, upper limit, the most optimistic case. Some chemical reaction may not be so fast, but this gives you an idea that normally at the surface of an AGB star, chemical equilibrium should be reached relatively fast. So in order to explain the deviations we find, we need some kind of process that departs the chemical composition from chemical equilibrium in a relatively fast time scale, okay? So basically, this is what I told you. So which processes may cause this departure from chemical equilibrium? So there have been many ones that were proposed. At the end, we have right now like a kind of two possible scenarios to explain this deviation, but the subject is not yet closed at all. One is the shock-induced scenario, which was mainly driven by Isabel Charsnev. This scenario is relatively successful in explaining some things, but not others. For example, these models, you can get high abundances for HCN and CS in oxygen-rich stars, but not for ammonia, for example. The formation of water in carbon-rich stars depends on whether which chemical network you adopt. And also there are some other complications that may arise that these models normally involve shock strengths of tens of kilometers per second. But when you go to look to the spectrum, this is an ALMA spectrum, at the very inner regions and the central pixel, you see line widths that are not consistent with such a high velocities occurring, okay? So the other scenario involves photochemistry, which has been worked by myself and also by Marie van de Sand in several articles. So also this scenario basically considers that UV photons arrive somehow to the surroundings of the AGB star, either because the atmosphere, the envelope is clumpy, and these UV photons can penetrate through it, because otherwise, normally, they would not penetrate because of the extinction of dust. Also, UV photons may arise from some companion that is close to the AGB star. Okay, so basically, this kind of models can enhance the abundance of these anomalously abundant molecules of water and ammonia in carbon-rich stars, of CS and ammonia in oxygen-rich stars. The main problem is that these models are relatively dependent on some parameters like the UV field and the clumpiness that nowadays for the moment are difficult to constrain from the observational point of view. So we don't know whether this can be the universal mechanism that explain all the departures from chemical equilibrium. Okay, some clues also may come from the observations with ALMA at very, very high angular resolution. So just looking at what's going on at the stellar surface. Here you have some example of silicon sulfide observed in a IRC plus 10^16, a carbon-rich star. But this, the interpretation of these observations is not straightforward. I mean, you cannot easily derive what's going on because first the region is relatively complex, this region. And also there are some complications arising, for example, in this case, because there is a radio photosphere arising from free interaction between electrons. And this hides what's going on in the few stellar radii, which is where the region where this non-equilibrium mechanism should be happening. So still, observations of this kind of this very high angular resolution should allow to put some constraint on what's going on, but it's not straightforward. So that concerning what's going on chemical equilibrium, I will now move on a little bit about to speak about dust formation, which we know that happens at some distance from the AGB star. Okay. So basically, this is the condensation course. You already have heard about that this morning. So basically, this just to put you in context, this is the distance from the star. So here we have the surface of the star at this typical temperature. We have here the carbon to oxygen ratio. So this region is carbon rich and this region is oxygen rich. And you have here the temperature associated, okay, with a given distance. So basically, you will have that if we move from the photosphere of the star farther away, at some point, in carbon-rich case, we will find that graphite will be thermodynamically stable. So in principle, thermodynamics tells you that in this region here, you don't expect at all dust, but from this distance, from this region to outer regions, thermodynamics tells you that graphite will be thermodynamically stable. So at some point it will condense carbon, okay? And the same for the rest of the species. In the case of oxygen-rich stars, you have here a plethora of species, but the one of the most interesting is alumina, that is supposed to be one of the main or the first condensates in oxygen-rich stars, okay? So here in this is all calculations according to thermodynamics, but at some point it will be interesting to know how this process of forming dust from gaseous particles, because we know that here dust is thermodynamically forbidden. So at some point dust should form from gaseous molecules, but how this process happens is yet to be understood. So clues to this. Again. Oops, sorry. Okay. Okay. So clues for this how this process happens may come from calculations. The first interesting point is to identify which are the most likely precursors. So the species, the gaseous species that will be the precursors to form dust. So here you have a case in chemical equilibrium calculations for the carbon-rich atmosphere, and where here basically what this plot is showing is where is carbon mainly located, and these calculations tell us that it's mainly located in this region in atomic carbon, but also in acetylene and carbon-3. Okay. So, and this is this shadow region is the region where, in principle, graphite is thermodynamically stable. Okay, so at some point here, dust should form from some of these species. So, there have been some experiments trying to simulate this process of formation of dust from atomic carbon in a experiment specifically designated to do that. And they found, of course, they found formation of dust, and they found some molecules that could be intermediates to the formation of that. Basically, the most interesting thing they observed is that they observed a lot of aliphatic molecules, but no aromatic molecules at all. So these experiments will be telling us that aliphatics will be intermediates in going from atomic carbon to the carbonaceous dust. Some other clues, moving for the oxygen-rich case, the interest here is trying to understand how this alumina is formed. In this case, we can again look at the chemical equilibrium calculations to see where is alumina located, and we see that it's mainly in atoms or these two oxides. So here there has been work at high angular resolution observations trying to identify and to characterize this aluminum oxide. These observations tell us that it seems to lock around 3% of the aluminum, which agrees with calculations, but still work is being done. And there has been also some very interesting chemical models trying to really follow the evolution from this aluminum to the dust, the alumina dust. Okay. I will speak in these 5 minutes a little bit about the outer regions, photochemistry. So basically, here you have these rings, very beautiful rings that were observed many years ago. Basically, this is telling us that these molecules are formed in the outer layers, because this is a kind of plane of the sky. We did the same more recently with ALMA at much higher spectral angular resolution and sensitivity, and basically we see the same, but with a greater detail. And in this case, we understand pretty well how these carbon chains are formed. They are formed basically in this process of polymerization, let's say. Basically, some precursor acetylene or HCN is photodissociated, and radicals are taking place in a chain of chemical reactions. And the rate coefficient for this reaction has been pretty well measured at low temperature. So this scheme is quite well validated. But now, in recent years, we have discovered with this telescope, which is in Spain, the JEVES 40-meter telescope, we have carried out a line survey of this carbon star, and we have found a lot of carbon chains containing metals, in this case, magnesium. All these guys, a lot of carbon chains containing magnesium. You see here, basically, in this case, the process we think these molecules are formed is because we have some magnesium that survives in the gas phase, is not completely on dust grain, survives on the gas phase at the level of a few percent. And then in the outer layers, it takes place in these reactions, reacting with cyanopolyenes, and then these cations recombine dissociatively with electrons and form all this family of molecules. Still, this scheme is not so well validated because the rate coefficients for these reactions are only coming from calculations. They have not been measured. Okay, a few words more on what happens really out the outer parts of the envelope. At some point, you see here in these plots that the abundance drop to 0 because all molecules, the small ones, are photodissociated. So it is interesting to understand at which radius this happens, because this is related with the photodissociation cross-section of each molecule. So if we understand well where each molecule disappears, this is telling us that we understand very well how each molecule is being photodissociated. So here, this work from this year of Saramasalhi was measuring this disappearance radius as a function of mass loss rate, and we found that when you increase the mass loss rate, this radius increases, which makes sense because the envelope becomes more optically thick, and then the molecules disappear farther away from the star. And this is connected exactly with what happens with photodissociation. Basically, these dotted lines are the predictions for a photodissociation model, and these are the empirical fits. So this is basically telling us that here in this region of high mass loss rate, all these three molecules photodissociate at the same distance, but when you move for lower mass loss rates, then they split in different according to their own photodissociation rate. So right now we are trying to compute the photodissociation rate of these guys because the literature is a bit conflicting and cannot fully explain what we observe. Okay, I will skip this. And just to finish, I will again show this because I mean we see this kind of ring, but also in the ring we see that it's composed of several thinner arcs that at some point they cross each other. So we think that this kind of structure can be explained by this binarity. But also there is a different process that also may shape the circumstellar envelopes at large scales. That is related, as you have seen also yesterday, that with the structure itself of an AGB star, which at some point the way the mass loss occurs is not spherically symmetric. You have seen yesterday the 3D models. So at some point, these inhomogeneities in the star itself and also in the origin itself of the mass loss process may shape at some point these convective cells you have here may shape the departure from spherical symmetry we see at larger scales. Here in this work, you see that when you go from the very large scales here and you start to make zoom and zoom and zoom, at some point here, which is the very inner regions, these departures from spherical symmetry at some point may be transported to the larger scale. So at some point, not only binarity, but also these convective cells may play a role in shaping these circumstellar envelopes. And just to finish, I would like to show these guys, which are my collaborators and which otherwise I couldn't have done anything. And with this, I thank you for your attention.
I have one. So what about S-type stars, or do we have too little information on?
Yeah, there have been less studies, but there are also some observational studies on S-type stars. And in that case, I would say it's more difficult because the S-type stars are just located at the carbon to oxygen ratio just 1. So normally you are in the transition, so it's not so clear to see whether the chemical equilibrium is fitting things or not. But yeah, there have been studies also on S-type stars. I mean, the most dramatic differences or discrepancies are found when you have really pure carbon-rich or oxygen-rich stars.
Is it generally true that the equilibrium estimates are sort of good for the high level abundance, and they sort of always fail on the low level abundance, or is that just the examples you've shown?
You mean if there is an issue of accuracy of the calculation, something like that?
Yeah,
in the low level abundance.
Yeah. Is it always the low abundance where the equilibrium estimates fail?
I mean, normally what we find is I don't think there is a problem of precision. I think the calculations are well because they depend on thermodynamic properties of molecules like water and these others that are pretty well known. So, and no matter where you look in the literature to these kind of predictions, they all agree. So it's not like with chemical kinetics that depending on the chemical network, you find very large difference. But here, I think there is quite solid and robust. What we see is that normally the biggest, I mean, the problematic cases happen always when a molecule is predicted to have a very low abundance, and then what we observe is a higher one. So I mean, it's something that at some point in these cases should break the main reservoirs to let some of these atoms to form other stuff. So to enhance the abundance of this. Still, I mean, there are these non-equilibrium processes, but we don't really know.
So the AH molecules, the polycyclics, made an appearance on your first slide, and then
yes.
I think nowhere else.
Nowhere else.
Can you say something about?
Yeah. Okay. Thank you. Thank you for the question. In principle, PAHs, I mean, they are observed with these infrared aromatic bands. And they are observed mainly in the post-AGB objects, not really in AGB objects. They have not been observed in AGB objects. but we don't really know whether this is because they are not there, so they are formed in a further evolutionary stage of post AGB, when you have your red giant becoming a white dwarf and injecting a lot of UV flux, or it could happen also that they are already formed in this AGB phase, but they are not properly excited because of the absence of UV photons. Because to observe these aromatic infrared bands, you also need UV photons to excite. Otherwise, you are blind. You cannot observe them even if they are there. So, but there has been a lot of work, and we don't really yet know whether they are forming the AGB phase or post-AGB phase. I mean, I think that my impression is that they are probably forming in the post-AGB phase due to the UV photons. I mean, when you have UV photons, you easily drive polymerization reactions that at some point you make things grow, either linear chains or some cycles. But this is a yet unexplored territory. I mean, there is a lot to be done to understand this properly.
So I'm curious, when we're looking at carbon-rich stars, what do you think would be the most impactful observations to sort of confirm or deny some of the ideas of chemical models? Like what molecule?
I mean, for the inner regions, all these things we don't yet understand. I think it will be ALMA observations at very, very high angular resolution. Because, I mean, right now, for the moment, there are not so many super high angular resolution with the resolution of the star itself to see what's going on. So that's my hope that in some years we will understand much better that due to ALMA observations. And also, if it would be possible to observe with the James Webb, but because of saturation effects, I think that will be problematic, but that will be also bringing a lot of information. But I don't have much hope on that.